So if we have 3 minutes for questions, it's usually fine, I think. But feel free to do 10 and then we can do more questions. Just sometimes the questions go slowly on the chat.
Mm-hmm. All right.
So, at the same time, I would like to remind everyone that you can ask questions via the chat function. I'll be monitoring that. And I will then, at the end of the talk, give you a chance to ask your question directly, or if you prefer, I can also read out your question. Please don't add your questions too late, because then I won't have a chance to curate them, basically. Okay, without further ado, Meike Zehlike will now talk about reducing disparate exposure in ranking, a learning to rank approach. The floor is yours.
Thank you. Yeah, thanks for the introduction. I'm Meike from Humboldt University in Berlin and the Max Planck Institute for Software Systems. And welcome to my home office. So I'm going to talk about a new learning to rank approach that is able to reduce disparities in exposure across groups. And this is what I'm going to do today, a little bit of motivation and a little bit of how the method works and a big chunk about the experiments that we did. So for those who are familiar with fairness in machine learning research, or maybe for those who are not familiar actually, there has been in the past decade a lot of attention to the fact that machine learning methods can actually reproduce and exaggerate biases in society. And there has been a lot of methods in ranking proposed for mitigating such discrimination and biases. And most of the early methods were so-called post-processing methods. So you were training a model, and then afterwards you would re-rank your predictions according to some fairness criteria. And in this motivation, I want to motivate a little bit to you why we need so-called in-processing methods, where you change the loss function of the learning approach such that it considers fairness criteria during the learning process. Okay, so why do we need that? It becomes a little bit more obscure, and post-processing algorithms are a little more easy to understand and stuff. But the problem is that they may actually be subject to legal issues, because you cannot just re-rank things that you don't like, results that you don't like. In many cases, there has been rules that prohibit that. And another problem is that these post-processing methods still allows a biased model to be trained and then deployed. And then you have to mitigate fairness according to some strict criteria. And these need predefined and hard-coded fairness constraints. And they may potentially ignore relevance judgments in total. And these combination of allowing a biased model to be trained and that hard-coded fairness constraints suggest that there is always an inherent trade-off between an optimally fair and an optimally relevant judgment. And we will see later in the experiments that this is not necessarily true. Okay? Now, very briefly about the method. So what we wanted to do is we wanted to construct a supervised learning algorithm that incorporates a fairness model into the learning objective. And we do that such we measure performance in terms of accuracy with respect to the training data. So that's the classic and standard procedure, and also in terms of how fair the result is going to be. And so we extended the loss function of listnet, reference anyway. So listnet is a listwise learning to rank method that was developed in 2007. And we extend that method by a listwise fairness measure, and we want to mitigate disparate impact with this. And this fair loss function now has two parts. It has an accuracy metric that we call L, which measures the error rate of the ranker F with respect to the training data. And we have an unfairness metric U, which measures the disparities of exposure for a ranking generated by F. And the disparities of exposure is meant in terms of when you have two different groups you can measure how much each of the group gets exposed on average. And if there is a big disparity, we want to reduce that disparity in the loss function. There's a lot more details in the paper, but basically the loss function looks like that. You have the accuracy metric, and you have the unfairness metric, and you have a factor that you can use to tune your algorithm towards more or less unfairness. If you set it to 0, apparently it's going to behave like the normalist net algorithm. Right. So the interesting parts are actually the experiments. And the first experiment that we did is, so we're going to see throughout these 3 different experiments that we have different types of biases in here. So the first experiment was on the W3C expert search data set. And that bias, we introduced a bias that was unrelated to utility. So the task there is to retrieve a sorted list of experts for a given topic. And we have given a corpus of emails that are written by possible candidates. And in this data set, we're going to consider women to be the protected group because they only make up 11% in the whole data set. And we sorted the training data such that we first had all male experts, and then second, all female experts. Then we had all male non-experts, and fourth, all female non-experts. So we injected a very strong bias against women while the expertise has been labeled correctly, then always when there were ties, we would break them in favor to men. So that has like a very strong bias against women that is not related to utility, okay? And what we should see in the results is that colorblindness, that means that we leave out the protected attribute, which is sex in this case, that should yield to the best results because the protected attribute is not correlated in any way with the expertise. Okay. Now, what happens when we train a standard ListNet algorithm on this data set? The colorblind result looks like this. So it sort of evenly distributes women and men across the entire ranking, okay? But once we introduce the protected feature, then what we see is that all women are actually ranked to the bottom of the list, even the ones that are experts, actually. And this is clearly not what we want because we're going to lose accuracy for that, okay? And then we also have a baseline of a post-processing algorithm that is called a FAIR algorithm, and it takes a parameter that is called P, and this parameter tells the user of the algorithm that I want to see at least 11% of the protected items throughout my entire ranking. And this, because this is a post-processing algorithm, that means I'm going to train the data, the model on the data set, on the entire data set. I'm going to use the protected feature as well. And then afterwards, I'm going to re-rank the predictions that the model will give. Okay? And then we see here that if we have a P that is close to the percentage of women in the data set, then it sort of fairly distributes women and men fairly well throughout the ranking. But if we choose the percentage to be too low, then nothing's going to happen. And if we choose it too high, actually, we're going to run into some sort of overcompensation. This is like an inherent thing that post-processing algorithms tend to do, that if you choose the parameters wrong, you might end up seeing stuff like that. And for our method, we also see that if our parameter gamma is a little too small, then we don't really do much. I mean, it's doing a little better than the other one, but not really. But the interesting thing is that no matter how high you set that gamma, you cannot overcompensate. So you end up coming back to a result that is close to the colorblind one that we wanted. Okay, now the second experiment is a different type of bias that is due to different score distributions. And here we have a list. The task is to sort a list of university applicants by predicted academic performance. And the admissions are based on a standardized test. That's PSU is a university admission test in Chile. And that is used at the high school grades. And then we consider students from public schools as the protected group because public schools tend to lag behind a little bit from the private schools. And now the interesting thing in this data set is that the bias arises from different PSU score distributions for each group. And that means that students from public high schools perform better than their fellow students when they have the same PSU scores. So on average, the PSU scores of public high school students are usually lower, but once they are in university, they actually end up performing better. And that means that the same PSU score does not correspond to the same level of academic performance across groups. And if you have such a bias, then just leaving out the protected feature, as we could do in the previous experiment, should actually yield to the worst result. Okay? Now, this is the same presentation of the data that we just had before with the bar plots. It's just a little more condensed. So what we see here is this is the result for the colorblind ranking. And we see actually, and the blue cross is the result for the standard learning to rank procedure. And we already see that the colorblind, as we expected, performs worst in terms of relevance and also in terms of fairness. So if we include the protected feature in such a situation, then we have a better relevance result and also a better performance result. And the blue dots are for the fair algorithm for the post-processing baseline, and the green ones are for the delta algorithm for our method that we propose. And what we see here is as soon as the method works asymmetric, and as soon as the fairness is already in favor of the protected group, then the algorithm doesn't do anything. It just behaves like a standard learning to rank function. Whereas the baseline is actually, if you set the percentage too high, then you might overcompensate and just lose relevance. You're not really increasing any fairness anymore. Okay, and then another situation or another setting where you might want to use such an algorithm is from the same data set, but in this time you want to optimize for substantive equality of opportunity. So as I said, the same data set, but this time we're going to consider women as the protected group because they only make up 20% of the admitted students. And on average, they have worse PSU scores than men, but better high school grades. And their performance after the first year in the engineering universities lags slightly behind. So what we want to do here is more of an enhancement of substantive equality of opportunity rather than relevance considerations. So what we see here is the colorblind result and the standard learning to rank result are sort of similar in terms of relevance, but actually the standard learning to rank procedure is exaggerating the fact that women are a little bit worse, and so it gives them even less exposure than they would have if they were in the ground truth. And again, we see that the delta algorithm performs similarly in terms of the fairness results when we compare it to the baseline, but it achieves a lot more relevance because it is not first model trained and then afterwards we enhance for fairness, but instead we consider these two measures at the same time, and it is easier to find the sweet spot between these two. Okay, so what we did here was we have seen now that in-processing methods have important advantages compared to post-processing approaches. And I presented to you one of the first in processing fair learning to rank approaches. We have seen that different types of biases call for different mitigation strategies, and the algorithm that we propose can handle all of those presented ones without a priori knowledge of which one it is. And we also saw that if we just leave out the protected feature, that can lead to the best or the worst results in terms of fairness and accuracy, which is important. Because there's a lot of literature that talks about an inherent loss of accuracy if you aim for fairness. And we have seen that if we aim for fairness in machine learning, it does not necessarily come with a loss in accuracy, but it depends on the data that we have. So that's it. Thank you. Any questions?
Thank you very much. Meike, we have one question from Han. What's the difference between colorblind ListNet and standard ListNet? Is the latter colorblind as well?
Colorblind ListNet means that you leave out the protected feature from the feature set, and standard ListNet means you use everything that is available. And when we talk about the protected feature, what we mean with colorblind is that we leave out those ones that are explicitly explicit about protected features. We cannot leave out the ones that are correlated with the protected feature. So there is like a very prominent example is that the zip code in the US correlates a lot with the race feature. And so you can leave out the race feature, but then what do you do with the zip code? Because it's not a protected category. And that's why colorblindness has been criticized a lot as well, because you say I'm ignoring it, but I'm actually not ignoring it because it is encoded in the other in the other features as well.
Great, thank you very much. We're moving to our